So, hello. Today I want to talk about mm, Morton curves, binary trees, quad trees, oct trees, whatnot, and finally about volume boundary hierarchy tree. Uh, why I want to do it? Because I'm doing a kind of simplish particle simulator as a like a project, right? And I have to calculate a lot of pairs of forces. So in this case, I can use, instead of brute forcing, it's a common technique. Basically, instead of brute forcing and calculating every pairs of nodes, in my case, basically, if it's kind of gravity-like force, it basically drops as an inverse r squared, and you might not want to consider further nodes because they are so far away that this 1 by r squared proportionality basically diminishes force to basically very small unimportant value, I guess, unless it's a very heavy object, right? So okay, and what you what you can observe when you're using these structures is that by, instead of brute forcing all the basically forces, it is faster to construct some kind of a structure which basically approximates clusters, basically approximates these points on different basic multiscale. And if you want to interact with some particle within a cluster far further away, right, you might not want to interact with it individually, but say you approximated this cluster as a whole and interact with the cluster itself because it's so far away. So right, so we need some kind of data structure, a way to implement this multi-scale basically structure. What else? And we can talk about a binary tree, because in the end it will be a binary tree. And let's just say you have some kind of points and you want to cluster them using a binary tree. And this is like a simple example. When you construct this tree with two branches, each node has two branches since it's binary, and there's a root node. In case it's a zero, it will kind of cover all the nodes, and then all the child nodes of this root node will segment the space into basically two parts each, and it will continue until it reaches so-called leaf nodes. Leaf nodes are in the bottom; they don't have any children. You get structure like this. Each node will basically contain information about how much space it covers and which are its children. We can basically apply this idea in 2 dimensions, kind of similar, and construct what's called quadtree. Quad, since 4, we have 2-dimensional space. We split it, we treat first root node as a whole space, then we split it into 4 pieces, like this, 1/4 here, and we split it again, each time dividing by 4 space. And so again, the idea is that when you say my particle wants to interact with all the other particles, let's consider this particle and start traversing, for example, this tree from the top. And by some criteria, you will say, okay, is this an appropriate level of approximation or not? So in this case, let's consider, okay, I want to interact with something. I'll check interaction with the root node, but the root node includes everything, so it's kind of rough approximation, if meaningful at all. And you say, okay, I will examine one of the quadrants, And here, for example, it examines the furthest quadrant, and then it say, okay, the criteria may be different, and maybe you will encounter or have encountered an algorithm called Barnes Hut for large-scale gravity simulation, and they pose a criterion how to determine if this level of refinement approximation is good enough, right? It will say, okay, how far is the quadrant, basically maybe its center, and how spread it is, right? Because let's imagine that you are examining the same quadrant, right? It's kind of close, but then it's very spread out. So it said, okay, it's too spread out. We want to refine it and examine inside, basically the contents. Oh, that I've implemented the same stuff. It kind of works, which is interesting. So yeah, the idea is that each particle will traverse this tree and determine at which level of refinement it will stop. So it's a nice approach. Again, I'm not expert, but it has some benefits, some draws. It uses a lot of memory, as I understand. Kind of, it's good for homogeneous data or something. That's why we will use another technique. And the question is, okay, what would you do if you didn't want to split this space in equal parts or something? So how would you impose some kind of structure for points using which you can start splitting the data? And here I give a like seemingly weird idea. Let's start with a simple kind of joke idea, is that we have some kind of points located on the circle, and then we have a curve that is parametrized such that passes through these points. And okay, what we get? What we actually get is that we have mapped our two-dimensional points into a parameter of this curve. In this case, it's t, kind of angle, maybe time, but time makes no sense in this case. I'm just accustomed to this. So yeah, each point from R2 is mapped, basically, not each, but in this particular case to parameter. And what we get is that we can sort. We understand that there's particular order in which these points, in which this curve passes the points. So in this case, you might say we have established an order that P1 should be first, and then the parameter increases, it passes P2, and so on. So we have established that this weird approach gives order to points. And now the question is, what about the clustering, right? And actually, again, this method provides way to measure distance. In this case, it would be an arc length, but we can see that distance between points P and 1 with parameters T1, T2, no, it's much smaller than distance between P2 and P3. So it kind of works. Unfortunately, it doesn't work because your data won't be on a circle. So yeah, what would you do? Like maybe project into a circle? It kind of makes no sense. Another kind of, if we expand this idea, we would say, okay, we make this spiral, and then in a sense, it will, if it's tight, it will pass all the points. At least they will be very close to it. But then you would question, okay, what about the idea of measuring this distance? So clustering by this parameterization. And of course, the points along the line will be, it will work. They will be close. But then if you skip from one spiral, the circle basically to another, you would say, okay, why is there a distance of basically 2 PR, right? So it's kind of an isotropic, kind of the same stuff if we do some kind of zigzag points along the line. the straights are cool, but on the sides not. And this idea of kind of trying to cover all the space with some kind of a line, these lines are called space filling curves. And actually we want to get some kind of properties that help us with this distance. So in this case, interesting idea is called Peano curve. It has the structure like this. In fact, here, and all these curves, they show different levels of refinement. You can watch 3 Blue 1 Brown video where he discusses Hilbert curve, why they wanted to do it. Basically, they want to create this curve or types of curve that you can refine, and at the limit, it will basically go through each point. It will cover all the space. But we will not use it. We will have a set refinement actually specified. So cool. What we get? Maybe okay. Let's examine the Hilbert curve from the video. And let's say we have this lowest refinement of the curve, and then we seed some kind of points, and the best we can get is that these points will clump to one of the points that is forming the curve. So what it exhibits some kind of truncation that we have to have. If we get the greater refinement of this curve is, the less truncation there will be. The closer the points will be to each unique point on this curve. And well, it's useful to notice that you can basically think of this distance as a arc length on this line. So 2 points will have some kind of distance, again, as we've discussed previously. What about the order? So in this particular case, we just consider that 1 point we should measure to distances to all the neighboring points in our space, which is like homogeneous, isotropic and such. And we see that it kind of works. It works to some extent. For example, these 4-5 points are kind of close in our space, but then if we think about arc length, they are still kind of close, except, well, yeah, this point to the right kind of sucks. But that's what we have to deal with. There is no universal approach to this. But as we refine more this curve, of course, it's kind of a fractal structure, so our total length grows. But something that Grant Anderson, whatever his name was, mentioned that the position of each point, kind of with respect to total length, it becomes more and more defined. You watch a video if you want to know why it's so. We won't use this property, but it's interesting approximation. Just the idea is that the more we refine, the more specific the position or the parameter becomes. Maybe what I wanted to kind of mention, it kind of makes no direct sense. The vibe is the same, right? Okay, if we return to our idea about the circle of our silly toy example, just think like the case when the space is subdivided. So we have some kind of discretization. In fact, of course, to some level, it always happens. So our curve will look something like this. And the points will gravitate, basically they will stick to centers of these kind of pixels. It doesn't have to be image, but maybe the idea is that also the parameters will be discrete. And even if you think about the you think, okay, it's a circle, we are working with floats which are like continuous. Even then, you must understand that basically there's a finite precision of how the number is represented. There will be a certain threshold when you cannot differentiate between two floats. It comes from basically, I think, how you represent it in binary. Of course, just the idea, you can't store infinite information, right? It's not useful, I guess, to have very much information. Okay, whatever. But the idea is what I wanted to tell you. Just there's some kind of vibe about this discretization, and we will come to it later. And that basically many points will map to one parameter. It's useful to know, but we won't encounter it directly. So yeah, we've examined like Peano curve, Hilbert curve, and the actual curve that's interesting for us is this Morton curve or Z-order curve. Guess why it's named Z order, right? But it forms such structure on the roughest level, and then we kind of refine it, but it still possesses this Z shape, and you can see it on many levels. It possesses this kind of quality again of basically local structure. You just consider one point and then think about the arc length to all the neighboring points. Yes, kind of locally it works very well. Maybe it doesn't work well in this case when we have a jump between these structures, but still, you gain something, you lose something. But what's more maybe interesting is how this curve is constructed, because we didn't talk about these curves. Not that we are very interested. We return the idea of subdivision of different levels of refinement. So you kind of refine your domain into powers of 2, which are related with binary of values of some binary length, let's say. So in this case, 3-bit value binary can create eight subdivisions, right? So you kind of associate your position in space with the binary value, and then each axis has this binary coordinate, and this strange approach is that you, for each point, you combine these two coordinates just by interleaving the bits, like on this example. So for every point. And what you can observe, okay, first of all, if you start at the corner 0, 0, you get 0, 0, 0, 0, 0, which represent, of course, 0 in binary, and on the farther end, you get something, whatever. Okay, 2 to the 6 or 2 to the 5, whatever number it represents. But and any intermediate values, you see that they grow from 0 basically to some maximum value in this fashion, and it looks something like an arc length in a sense, right? But definitely there is order. The curve has some kind of local structure, and it's very nice. Basically, okay, here's an example. What I did is I've generated some kind of list of points, and I created these polygons basically just to show you the order that I generated them randomly, right? I transformed them. I added additional attribute of this Morton encoding, where you basically transform it into a number, something from here. I sorted by this parameter, these points, and then I plotted again this basically polyline, I don't know how to call it. And what you can observe is this structure. It is not exactly so. We can discuss it briefly. It is not exactly like this beautiful structure. Basically, how I interpret it is you have your points, they're somewhere in space, but then there's the truncation happens. You represent it in some binary length, which again depends on how many subdivisions here you make. And of course, you have basically some kind of truncation. So, okay, what happens is that these points kind of in these Morton representations are being like gravitated. They are truncated to the nearest point of this structure, but they don't kind of, it's only representation that switches. But basically, yeah, and then you can sort it by this representation, and then you basically reconstruct this order. You relate it to the original points, and you get some curve that looks like this. Again, the positions didn't change, the ordering has changed. At least we have established this ordering, and that's what happens here. So first of all, there's no like clear structure, because depending on how you chose to convert them to Morton code, with which resolution it will have, it may have very tiny structures. So first, it will be truncated in Morton code to the level of structure, to the lowest. And the second, it just doesn't, the point don't change actually. So there are basically multiple factors why it looks like this. So it's subsampling and the basically order of this approximation. So again, let's repeat that we have ordering and we have something that helps us to form a structure. That's cool. And it's one-dimensional. So the idea is that we have mapped 2 dimension to 1 dimension, and we can apply a binary tree to start segmenting it. And the idea of using this Morton encoding and forming a binary tree, it is exploited, it is used in this particular paper, which was published in 2012, which discusses how to do it in parallel fashion. It was important for me because I wanted to implement it on a GPU. But again, the basic version is applicable to also the CPU. But we will discuss the GPU. We will discuss the simple version and then the GPU implementation in particular, because it has some interesting properties. How this distance, arc length, and such, how it relates to it. So okay, cool. We have order, but how do exactly we measure distances? Basically, how do we decide these splits? And the simplest idea, similarly to the Quadtree, where we split the space into 2 parts. Each time we subdivide. Here we propose something similar. So this is the binary representation. It is sorted in growing order. Of course, each binary, this vector, it represents some kind of, in this case, unsigned integer, which is a kind of a sum, which shows which some basically parts are included. And you just say, okay, we subdivide this at first we have a root node. It will contain all the nodes, and then we will subdivide it into two parts. One part will contain half of the curve, other part the other half. Maybe what's cool here comparing to Quadtree is that we just work with data which we have. So we may have only one point on the left part, in which case we won't have to subdivide any further, and maybe all other points on the right part. Maybe it was referred as balancing or something. Okay, whatever. And so the first step is subdivide this older region into basically two parts, and of course we do it by the first leading bit in this case. Byte, bit, okay, whatever. So in this case we have a number that is binary value that is encoding from 0 to 31, I guess, so 32 in total. And we say everything that is larger than 16. So this first bit represents if the number is larger than 16. It will be split into one node and the other half, as you understand it. And then we basically repeat this for each children node. So maybe we want to repeat it on a second line, but then we have all the same bits. Values, of course, we can just include this into our first subdivision and then work on the next level. Basically, again, we repeat the same procedure where the two numbers are different, and we can repeat it, and we get this particular structure. Okay, and this top-down method, it's easy to understand, but it's not properly parallelizable, because as you can imagine, if you want to work on some node, so you say this node, it spans some region, and we want to start subdividing it, you actually have to know what this region is. Basically, you have to know the neighboring nodes and where they end. So when you start from the root node, in order to start working on the next level on the right node, you have to know what is the left node, and so it's sequential in its nature, and it's not properly parallelizable, so it will not be fast. So yeah, the paper then asks, can we actually construct such approach when we can start bottoms up? And well, the idea is that we start exploring the leaf nodes at the bottom, and then we try to, from each leaf node, somehow construct an intermediate node. Again, intermediate, it's not leaf, something above. So yeah, and in fact we can do it by using the properties of binary trees and the fact that we are using Morton code and that values are sorted. Kind of, it's based on observation. They are sorted in a sense that allows us to take one node and then examine its neighbors and know that it's it's an order, basically. Maybe left neighbor is close, maybe right neighbor is also close or far. You can start basically examining them individually. And then there was observation that for this binary tree with n leaf nodes, there are n-1 intermediate nodes. I don't know like the exact implication of this, but the idea is that maybe you can start working on each leaf node, at least n-1 nodes, and try to reconstruct individually each intermediate node. For example, 4 leaf node will construct intermediate 4, 3, 3, and so on. So in a sense, that's how we are expected algorithm to work. And the question is, how do we do it? Because how do we know how to do it, basically, if we don't communicate with all the other nodes? It's a good question. And that's where these interesting ideas come in. But everything spans from this idea of basic distance to nearest neighbor, and like the order of this distance. So paper produces you the algorithm. First, we will just discuss it as basically in words. So for example, you do it in parallel. You pick some node, say node 3, leaf node, and then you ask, okay, I examine its two neighbors, left and right, and I try to understand if it's more like this selected node or it's not. Basically, likeness here in this case means if they're close or far away, because you want to start clustering the neighboring nodes. So okay, in this case of node, again, how you do it? Basically, the paper authors say we can compare how many common bits are the top bits between two nodes. Basically, if two nodes are close together, they will share these larger values, first bits, and only differentiate in the bottom bits, which give basically smaller values to this sum in which it's represented. Okay, so we compare it to the right node. How alike they are, basically how many bits they share in their head. We will refer it as a head length. So we see that between 3 and 4, basically there is maybe between 2 and 3, we see that they share 4 bits, 4 entries, and the neighboring, they don't share anything. And if you view it in a number representation, of course 4 and 5 are close. They are only different by this 2 to the power 0 contribution, and we don't compare it with 19. So it says that to the left we get a node that is very much like Q, and we are interested in this direction, basically in which we will search nodes that are similar to us. And we can, of course, we can easily do it just by difference between nodes, basically head length. 0 minus 4 produces minus 4, and that means the distance will be measured like to the right is the positive direction, and you take a sign, of course, like minus, it means that we will traverse to the negative directions and search for nodes that are like this node. Because again, I have to reemphasize, we are not constructing two nodes, construct one parent. In sense, it's not such case that we are not constructing this kind of structure. There may be jumps. In some cases, intermediate node will have another child as an intermediate node and a leaf node and such. So it's kind of more involved. And what we must also understand, that the span of this node, basically where it covers, it may be very large. It doesn't even mean that node 3 will be a child of leaf 3, will not necessarily be a child of intermediate 3. So okay, we've established that we can determine the direction. And the question is, like here, for example, we are trying to construct node 3 that will span to the opposite edge. And how do we how do we know how far we should go? And we will solve it using this idea. So yeah, our neighboring node is kind of like us. Other node is unlike us. So idea is that if we measure the likeliness, the head length of a node that is not like us, and say, okay, we go in direction of node like us, and we will take all the nodes that are better than the opposite node. So let's, I don't know if I should repeat it, but basically in this practical example, we were working on node 3. Node to the right, node 4, shares common head of length 0, and we say, okay, we will traverse to the left and pick every node which has a better match than length 0. So it kind of chops off it kind of includes the comparison to the other cluster in a sense. And that's what is done. In code, basically, the distance I've explained it. Basically, this delta minimum is a head, like how similar is this node to its unsimilar neighbor, and then we want to traverse in the direction d, in this case in the left, in a negative side at some steps, and include all the nodes that are more like this other node, which is unlike you. I hope you understand at least the idea. And what you get is this the opposite edge, basically where the range of a node ends. So in this case, we have selected everything because every node has a head larger than 2. And basically this will be our j. We started from I, and we measure again how similar are these nodes. Basically, what's important here is that by this procedure we have established the bounds of the intermediate node 3, starting from I to j. And the next question is, we can actually subdivide it. We can determine its children. We can determine where to subdivide it. And here the idea is completely the same as we've done before. Again, we will compare the leading bits. And for it we say, it will kind of, okay, we will say, okay, we will compare our left and right bound, and we'll say, okay, they are at least this similar with this delta node ij mean. And the paper, it's kind of tricky to explain it, but because nodes are ordered and they share the common head after subdivision, some form of common head, it's kind of tricky. Maybe I will just show you in a publication. So this part. So delta ij is kind of it shows that all this range share at least this big common head. And well, this part, when we take some other subset of this of this range, basically it will be it will have at least the same common head. It's kind of tricky to understand, but the idea was the original is that we will traverse and look where the head starts. It changes basically abruptly, something like this. And so this is the idea. I will not examine the code, but basically we will say, okay, the minimum common head for this segment is this. So it's a, in this case, head or between difference, basically common head length between node 3 and the other side, which is node 0, is 2. So we see, so we see this part shared. And basically we want to start at 3 and start traversing to the left and searching for when this minimum bound will be encountered. So in this case, it will step to the right. You see the common head is 4. It's much better than a minimum bound, which is 2, but then it will jump to 1, and suddenly the common head becomes 2. So it's a signal that there's some shift in this distance representation, and that we have to actually put a split here. There's one caveat that depending on the direction which we are traversing, we might include or not include this index. It will be shown here. Basically, I've manually gone through this algorithm. Of course, I have also programmed it, at least I have copied implementation in C++ and verified that it kind of works. But here I just put the steps just manually and examined node 3. And what we get is we get this J. It's an opposite. It's an index of opposite side. Here, this common head. Basically, we start traversing in. They are using binary search, so that's why it's kind of complicated. But we are traversing from the I in that direction, and we are looking when we will reach this minimum common head, which would signify the split. And then we remember this position split. And this gamma actually is the position of the split, which includes whether we want to include it. Basically, it just the countdown is set up as this. So if we include -1, if we skip or not. And actually, that's good. We've determined the node bounds. We determined where to split it. And now the question is, how do you determine which nodes are split in? Because we have no information about what other nodes are doing. And I don't understand how it's implemented. For me, it's kind of voodoo magic. But I guess the structure of this particular tree, the fact it's Morton, it uses Morton code and it's binary, and I guess it somehow allows them to determine whether the child would be either intermediate or leaf nodes. But then if you just tested this if-else comparisons, you will see that a node 3, it has a left intermediate 1 and a right intermediate 1, which is exactly what we see here. So this part I completely don't understand. It's a magic. But then we have examined this kind of semi-trivial example where the node spans completely to the left. So what about like this case, right? Because here we actually had a strong separation, such a rough, strict, and it's not the case between 2 and 3, which are 4 and 5 and 3, right? It's not apparent. But basically, yes, you repeat the same idea. You compare left and right neighbor and determine the search direction. And then you determine, okay, I want my good neighbors to have at least the same head size. So at least the same similar, I mean, better than the bad neighbor in that sense. And then we start traversing and looking for nodes which have common head greater than 2. So in this case, it will take 4. It will try to compare to node 4, but it has 0 length. And 0 is less than 2. And it will actually stop here. So we have determined the j, the bounds. And actually there's the idea that we have only 2 nodes in this list, in this range, so we don't have to, we already know where the subdivision is, but formally in this algorithm we get the left bound, the step in a positive direction, which leads to opposite end. And then if we examine this algorithm, which searches for split step is 0, so we get that we split after node 2 from which we have started. And then we do this if-else check and realize that for intermediate node 2, we will have left and right node, leaf nodes 2 and 3. And well, as if so, with some magic, that's actually what happens. So final time, I will repeat the procedure. We search for direction from unlike node to like node, and then we start expanding our region to be better than unlike node. And when the region is expanded, we were searching for split position, again based on when the common head will have this abrupt jump. So as I've said, this delta ij is a minimum common head, and at some point it will reach this minimum, and we are searching when it will reach this minimum. And what this enables, again, and plus some magic, it enables to construct this bound. It's not yet boundary volume, but it's a radix tree, I guess, in parallel fashion, which is amazing because it's very fast, especially if you have a lot of nodes. So let me do a simple demonstration. So I've been programming this particle simulator. So in this case, I have 1024 particles, but it's largely depends because it happens in real time. It largely depends at which frame rate I want to render it. Maybe I want to reduce the time, but then it's visually not pleasing. But yeah, so in this case, each particle actually interacts with all the other particles. And so you see this kind of gravitational interaction, which is interesting. It turns into complete chaos for many reasons. It depends on like how you integrate. And of course, it is based on construction of trees. So each frame or each n frames, depending on whether you expect particles to move a lot, it will construct this crazy binary tree. But in this case, it constructs. It has to work with the volumes, right? So it uses bounding boxes. So yeah, I find it kind of cool, and I don't know what to tell you more. I don't know. Can watch this. So I guess that was it. I think it was interesting use of this binary world, which I'm not completely not used to, and I hope that you learned something. And yeah, see you in something else, some other random video.